Hello friends, so today we are going to solve questions from rotational motion and these questions are from the year 2021. We are going to solve total 12 questions and all these 12 questions are from the mains. And for this 2021, it is part 1. Remaining questions of 2021 we are going to solve it for part 2, in part 2 rather. So the first question, it states that 4 equal masses each are placed at the corners of a square of length as shown in the figure. The moment of inertia of the system about an axis passing through A and parallel to DB, which is a diagonal, would be. So basic figure is given to us and we have to find out moment of inertia which is passing through A and that is parallel to DB. So we can approximately draw that this is our axis about which is passing through point A and is parallel to our DB. Okay. So we can just, in this case, there are two ways of doing it. One is more traditional way by using the coordinate. We will try that method first. And the second one is using the basic principle of our moment of inertia, that is our mass into perpendicular distance and its square. So let us say that our A is our origin and its coordinate are 0, 0, 0, and our B is having a coordinate over A 0, 0, and C is having a coordinate of our 0, A 0, and D is having coordinate of our 0, A 0. One second. C is having A0, A0. Sorry. Okay, so let me write it here that A is having a coordinate of 0, 0. B is having a coordinate of A0, 0. C is having a coordinate of A 0, and D is having a coordinate of our 0, A 0. We are mainly interested in the diagonal. Okay, so diagonal is our B and D points. Okay, and the axis of rotation is our moment of inertia is about with respect to A, which passes through 0, 0, and 0. So first of all, let's find out what will be our axis of rotation. Okay, and the axis of rotation is given parallel to our dB. Okay, so first of all, let's find out our dB. Then from that we can find out what will be the equation for our that passing through point A. So we can say determine axis of rotation, and we are having a diagonal dB and which is basically from 0a0 to a00. So from here we can find out its direction vector. So we can say direction vector of dB which can be represented as dB vector, and that will be given as our a minus 0, comma 0 minus a, comma 0 minus 0, and which comes as our a minus a and 0. From here we can easily find out the unit vector along dB. So we can say unit vector along dB, and let us call this as u unit vector, which will be equal to our a minus a0, that is a vector dB, and divided by the magnitude, which is our a square plus minus a square plus 0 and its square root. Therefore we can write that our unit vector will be equal to our, this will be coming as a minus a 0, and we have this as 2a square, which can be written as 1 upon square root of 2 divided by 1 upon square root of 2, this is minus comma 0. And therefore we can say that the axis of rotation passes through a coordinate 0, 0, 0 and parallel to unit vector u, and parallel to unit vector u. Now we can use the basic formula for moment of inertia, and we know that moment of inertia of point mass that is of I is equal to summation m of I r of I whole square, and this I goes from 1 to over n number of point masses are there. Okay. And we have to remember that this is the important part here is the perpendicular distance to the axis, which is our nothing representing our Ri. So we can say that perpendicular distance to the axis and so if we are having a point r whose coordinates are given as x comma y comma z, and we can write the perpendicular distance to an axis through origin and direction vector with suppose given as our d, and that is equal to our d of x comma d of y comma d of z, and we can find out that our r will be equal to cross product of and its magnitude divided by the magnitude of our that direction vector. Okay. And here the axis passes through the origin, which is A, and is parallel to the equation, which is given as A minus A and 0. Okay. So from here we can write that axis passes through A, which is 0 comma 0 comma 0, and parallel to that is our d vector, which is our A minus A and 0, and we can just find out their cross product with respect to respective masses. So we start with mass at A. And its position vector which is supposed represented as r of A will be over 0 comma 0 comma 0. Therefore the cross product, that is our r of A cross d, will be equal to 0 comma 0 comma 0 cross A minus A and 0. Obviously it will be equal to 0 comma 0 comma 0. Now we come to the perpendicular distance, that is our distance RA. General formula we have already written for it, that is the cross product, its magnitude, and our direction vector magnitude. Cross product we found out is 0, and the magnitude of d will be over a square plus minus a square square root, which will come equal to 0. So it means the moment of inertia, that is our I of A, will be equal to mass r of A whole square. R of A is 0, this comes mass equal to 0, so moment of inertia contribution because of mass at A is equal to 0. Similarly, we are going to solve for each part. Now we are having mass at B, and mass at B is our 0 comma 0 0. So its position vector, that is our r of B, will be equal to our A comma 0 comma 0. Now we come to the cross product, can say our RB cross D will be equal to A comma 0 comma 0 cross D is our A minus A and 0, and this cross product will be coming as our 0 comma 0 minus A square. And we are interested in its magnitude, though we can say RP cross our D, and its magnitude will be equal to 0 square plus 0 square, and this plus minus A square whole square and its square root. This will be equal to our A square, and we are left with then the distance that is our R of B will be equal to a cross product magnitude and our magnitude of D. Cross product magnitude is our A square, and D will be equal to our A square plus minus of A square and square root, which will be coming as our A square, and this will be our 2A, square root of 2A. So, and this A goes by this square, so we are left with that our R of B is equal to A upon square root of 2, and its moment of inertia, that is of I of B, will be equal to mass and distance square, which we get this as mass A square root of 2 whole square, giving us ma square upon 2. Now we come to our C. So we can say mass at C, and it is given as A comma 0. So the position vector, that is our R of C, will be equal to A comma 0. Now we come to the cross product. R of C cross D will be equal to A comma 0 cross, we have A minus A and 0, which will be coming as 0 0 minus 2A square. Now we are interested in its magnitude, so this comes as RC cross D, and its magnitude will be 0 square plus 0 square plus minus 2 square whole square and its square root, which will be giving us as 2A square. Now we come to the distance, because our D will be our same. So we come to our, one second, D is our A square plus A square, yeah. So we can say that our distance RC will be equal to the cross product's magnitude, and this our D magnitude will be coming as 2A square divided by A square root of 2. Square goes by this 2, and we can rationalize it, and rationalization will be giving us A square root of 2. So therefore its moment of inertia, that is of IC, will be equal to mass and distance square, which comes as mass a square root 2 whole square, giving us 2m a square. And finally we have mass of D. Mass at D, which is our 0 a 0. Position vector we can write as r of t will be equal to 0 a 0. Ideally we should have written as in the form of I unit vector, j unit vector by k unit vector, but that is not going to change any of the calculated part. And we can find out its cross product, that is our r of t, and we are left with this 0 comma a 0 cross, we have this as a minus of a and 0, which gives us 0 0 minus a square. Now we are interested in its magnitude, so we get r of t cross d, and its magnitude will be equal to 0 square plus 0 square plus minus a whole square and its square root. So this gives us a square. Now we can find out the distance, that is our d distance will be equal to our cross product magnitude and our d magnitude. This comes as a square, and it will be a square root of 2. Square goes by this, and we are left with a square root of 2. Therefore id will be equal to mass rd square, and we are left with this as our m a square root of 2 whole square, which gives us m a square divided by 2. So total moment of inertia will be summation of individual moment of inertia. You can say total moment of inertia, which is suppose is I, will be equal to IA plus IB plus IC and ID. And IA is our 0 and IB is our MA square by 2 plus 2MA square plus MA square by 2. And 2 we can take as LCM, so this becomes 4 plus 2 is 6, so this will be coming as 6 by 2 MA square, and 6 goes by 3, so we get total moment of inertia is equal to 3MA square. So it is our, okay, length is L, so this becomes as 3ml square. Okay, let me put it here. So and this is our 3ml square. So option 3 is correct. Correct. Next question. It states that consider a uniform circular disc of radius 0.2 meter. It is pin supported at its center and is at rest initially. the disk is acted upon by a constant force F 20 Newton through a massless string wrapped around its periphery as shown in the figure. Suppose the disk makes n number of revolutions to attain a angular speed of 50 radians per second. The value of n to the nearest integer is given that in one complete revolution the disk rotates by 6.28 radian. Okay, basic figure is given to us. So we have a disk which is pinned at center C, and you can say force of 20 Newton is applied to a massless string, and this massless string is you can say wrapped around the disk. So obviously it is going to, you can say, rotate the disk. And for this we can make use of our, you can say, energy conservation, or some, it is also called as a work energy theorem. Okay, so we can make use of our work energy theorem, and it states that the work done by the torque, because this force is going to produce a torque, is equal to the rotational kinetic energy gained. Okay. So we can say that the work done by the torque equals the rotational kinetic energy. Rotational kinetic energy, or mathematically we can write it that work done, suppose, is W, is equal to over half I omega square. And work done also can be represented in terms of the angular displacement. So we can also say that our work done is the torque times the angular displacement times the angular displacement. Or we can say that our W is equal to, suppose it torque is our tau, angular displacement is our theta. Okay, and torque, this torque we can easily find out. We can say our torque tau is equal to force multiplied by the perpendicular distance. Perpendicular distance will be here the radius. Okay, it is going to move in downward direction with the omega. So we can say our force is our 20, and our radius is given to us as 0.2 meter. So this comes as our 4 Newton meter. Therefore we can write that our work done W will be equal to 4 times theta. Now we have our kinetic energy, that is our half I omega square, because this is nothing but our kinetic energy. Therefore we can say that our kinetic energy is equal to half I omega square. I is a moment of inertia. We can put its formula, it is standard one, is our half mr square multiplied by omega. And radius we already know, so this comes as 1 by 4, and this is a mass 0.2 whole square and omega. And omega is also given to us, that is our 50 radian per second. Okay, and it is omega square. So let me substitute it here. This comes as our 50 whole square. So we get our kinetic energy will be equal to 25 times m. Okay. Now we are having two equations of our work done. Work done is equal to 4 theta, and work done is also equal to 25 times m. So let us call the equation number 1 and equation number 2. So we can say from 1 and 2 we can write that our 4 theta is equal to our 25 times m, and from here we can say our theta will be equal to 25 m upon 4. Now we are given that it is having n number of revolutions. Yeah, n number of revolutions. So you can say for n number of revolutions, we can write over that n is equal to theta upon, for single revolution, that is 6.28. Theta we already know is our 25 m upon 4, and this is 6.28, and m is also given to us. It is 1 second. Mass is not given. Oh yes, mass is not given to us. Anyways, we can, we can say, just write the final equation for n, that our n will be equal to, this will be coming as 0.9952 times m. Okay. And if the value of m is given, we can just find out n. Okay. So we need to solve it by using other approach also. For that we are going to use angular acceleration. I think that is going to, so it is having angular acceleration of alpha. Okay. I didn't check that mass is not given to us. And okay, let's start with angular acceleration. So we can say our angular acceleration, that is alpha, will be equal to torque upon moment of inertia I, and we are given that torque we found out is our 4, and this is our one second. Moment of inertia is our half mr square. Okay, let me write the formula. So torque is equal to force into our radius, and this is our half m r square. So this r goes by square, and we get this will be equal to 2 times f divided by m times r. Let's substitute the values. We get our alpha is equal to, this is our 2 times force is our 20 Newton, and mass is given, I think. I'm not. I think I missed somewhere. Mass. Let me check. I think mass should be given to us. Otherwise, we cannot solve it using the second part also. Yes, mass is given to us. It is considered a 20 kg. Here it is written 20 kg. I missed it. So there is no need to solve it by second approach. Okay, this is not required because mass we know is our 20 kg, and that is going to solve our purpose. So this comes as 0.9952 multiplied by 20, and this comes as 19.904, approximately can be written as 20. Okay, so the answer is 20. My apologies, I missed this 20 kg. Okay. So there is no need to solve it by the second approach. Okay. Answer will be no doubt will be coming same. Okay. It's not going to change anything. Next question. It states that a force F 4I plus 3J plus 4K is applied on an intersection point of x is equal to 2 plane and x-axis. The magnitude of the torque of this force about a point 2, 3, 4 is round off to the nearest integer. So here we have to remember that the force is being applied is at the intersection of x is equal to 2 and x is equal to x-axis. Okay. Therefore, we can say that our first of all we have to identify the point of application of force. Point of application of force, and we are given that it is intersection of intersection of plane x is equal to 2 and x-axis. So for x-axis we can write that x-axis has points. The general equation we can write this as our x 0, 0, and we are having a plane, and plane is our x equal to 2, and this plane is defined by x is equal to 2. So therefore the intersection will be occurs at x equal to 2 and y is equal to 0 and z is equal to 0. So it means the point of intersection is solely going to lie on the x-axis. Okay. Therefore we can write that point of application let us call this as R application will be equal to 2, 0, 0. Now we have to find out the relative position vector relative to the given point. So you can say that position vector relative to the point, and we are supposed to calculate the torque with respect to the point, that is 2, 3, 4. We are given that torque is calculated about 2, 3, 4. Therefore the position vector that is our R will be equal to that is 2, 0, 0. So this comes as 2 minus 2, 0 minus 3, and we have 0 minus 4, which will be equal to 0, minus 3 and minus 4. Now we can easily find out the torque based on the cross product of force as well as the position vector. So you can say our torque tau is position vector R cross the force F, and we can write it as our I J K, and we have this as 0, minus 3, minus 4, and we have 4, 3, 4 is the force, 4, 3, 4, and we get that our torque will be equal to this comes as minus 12 minus 12 plus 12, which will be giving us 0. So this comes as 0i. This will be minus j, and it will be a minus of 16. That comes a plus of 16. And sorry, not plus of 16. This will be 0, 16 minus 16, and it will be minus of 16. And then it will be plus k, which will be equal to over plus of 12k. Therefore, we need to find out its magnitude. So we can say that its magnitude will be equal to 0 square plus minus 16 square plus 12 square and its square root, which will be coming equal to as 20. Next question. It states that a solid disk of radius a, mass m, rolls down without slipping on an inclined plane, making angle theta with the horizontal. The acceleration of the disk will be 2g sine of theta divided by b, where b is. And okay, basic figure is given to us. Solid disk, it is rolling downward, so there is no slipping, only pure rolling is there. So we can say there will be two type of forces that will be acting on the, rather we can say three forces, but we are only interested in two forces. One will be the component of the mg, and other one will be the frictional force, which will be giving us a torque. So if, okay, let me draw it. So we are going to have our mg downward direction, and let us assume that this center of mass acceleration is capital A, and the angular acceleration is suppose alpha, and this angle is given as theta. Therefore we can write, because it is without slipping, so pure rolling, so we can say for rolling we can write our linear acceleration of the center of mass A will be equal to our angular acceleration, that is our alpha, or we can say that our alpha is equal to A upon small a. And here A is the radius. This is our radius A. And mg we can divide into two components. So this angle will be theta. So we are going to mg cos of theta, and we are going to mg sine of theta. And there is a frictional force which will be acting in upward direction. And So we can use that for linear acceleration A, or linear acceleration A, we can write that our mg sine of theta minus frictional force will be equal to mass into linear acceleration A. And then there is a rotational part. So we can say our torque equation or rotational motion. Torque, or we can say our rotational motion, and we can say our torque tau will be equal to our frictional force and our acceleration, angular acceleration alpha. Okay, and the moment of inertia of I is our half m a square. We know the relationship that our tau is equal to I times alpha. Therefore, tau is our f alpha. So we can say our f alpha is equal to I is our 1 by 2 ma square, and this comes as multiplied by our, this is f times a, radius a, and alpha is our linear acceleration divided by radius of a. So from here we can say that our this a and this a and a cancels out, so we get this equal to over half m a. Now we can, let us call this equation number 1. So we substitute f in equation number 1. So you can say from equation 1 we can write that our mg sine of theta minus half ma is equal to m times a. And we solve it, and our mass cancels out throughout. We get our g sine of theta is equal to, this will be coming as a plus a by 2, which will be coming as 3 by a. Therefore, acceleration a will be equal to g sine of theta, and divided by, this will be our 3 and this comes as 2, and this acceleration, the equation is given to us as 2g sine of theta divided by b. So from here we can say that our b is equal to over 3. B is equal to 3. And this, okay. Next question. It states that a triangular plate as shown, a force F 4I minus 3J is applied at a point P. The torque at point P with respect to point O and Q are. So basically we are given an equal triangle and force is being applied at point P. We have to find out the torque of point P with respect to first as O, then with respect to as Q. And let us denote it with respect to the coordinates. So we can say O is, let us suppose our origin is our O is our origin, which is 0, 0, 0, and our Q is on x-axis, so this comes as 10, 0, 0. Okay. And for coordinate of P, we should be knowing the height of point P. Okay. So the height of point P is, let us suppose, as h. So we can say that our h will be equal to, this comes as square root of 3 divided by 2 and multiplied by a. A here is 10. So we get square root of 3 divided by 2 multiplied by 10, giving us 5 root 3. And obviously other point will be, this distance will be 5. Therefore we can write our P will be equal to 5, 5 root 3, 0. We are given force vector, so we can say our force vector F, it is given as 4I minus 3j, and which we can write as 4 minus 3, 0. And the entire, you can say, system as well as force is xy plane. Okay. Or we can see also that our force is not having our any z vector. Okay. So from here we can just draw a conclusion that our torque will be acting along z axis, which we are not asked, but still we can just make. So we have to find out the torque with respect to 2 points, point O and point Q. So let us start with point O. So we can say our torque about point O. And let us call this tau O will be equal to position vector of our OP cross product with our force F. So let us find out our position vector OP will be equal to our 5, 5 square root of 3, 0 minus 0, 0, 0, which comes as 5 root 3, 0. And we can write that our tau naught will be equal to 5 root 3, 0 cross product 4 minus 3, 0. And this will be giving us, we are only interested in magnitude, no need for the direction. So we can say this will be equal to our minus of 15, and this comes as minus 20 square root of 3 minus 15, 20. Okay, it looks like option 1 should be the correct one, but let's try for our torque Q also. So we can say torque about point Q formula will be same. Torque Q is equal to R QP cross F. So we can write the position vector QP will be equal to 5 root 3 0 minus, and Q is our 10 0 0. So this comes as our minus 5 root 3 comma 0. Therefore torque with respect to point Q will be equal to minus 5 root 3 comma 0 cross product, and this cross product is our 4 minus 3 and 0, which comes as 15 minus 20 root of 3. So therefore option 1 is correct. Correct. Next question. It states that mass m hangs on a massless rod of length L which rotates at a constant angular frequency. The mass m moves with a steady speed in a circular path of a constant radius. Assume that the system is in steady circular motion with a constant angular velocity omega. The angular momentum of m about point A is LA, which lies in the positive z direction, and the angular momentum of m about B is LB. The correct statement of the system is. So basic figure is given to us. It is moving in the radius r, and we are having angular momentum over point A and angular momentum over point B, and they are with respect to find out whether it is constant and with respect to magnitude as well as the direction. And so we are given that our vertical axis is z direction, and so we can assume that the circle is representation of basically xy plane. Okay. And basically this results in a conical pendulum. Okay. This we can call as a conical pendulum. And let us consider this point A as origin and mark its coordinate as 0, 0, 0. So we consider that the center of circular path, which is our A, and we assume that it is having a coordinate of 0, 0, 0. And the conical pendulum length is given as L, so we can write that our radius of circular path that is our R will be equal to L sine of alpha, and we can say that our height of the in this case, like I said, that since the rod's projection in the xy plane is the radius of the circle. Is the radius of the circle, and we can also say that our this height of the mass which is basically the z coordinate, we can write z is equal to minus of L, and this comes as cos of alpha, and okay, we will deal with that later on. And it is given in the figure that point B is directly above point A, and the height is h, so this height is our h. Therefore, we can say that our point B is directly above A along z axis. Therefore, for B we can write 0, 0, h, and we can write our position vector for our mass m. So we can say the mass m at position, let us suppose that is our Rm, and we can write its position as we are having this as R cos of omega t, R sine of omega t, and is our z. Okay. And R and L we already know, R and Z we have already defined it. So this is our z, and where is my R? Here is my r, L sine of alpha. So I can write that my r is equal to L sine of alpha, and my z is minus L cos of alpha. Now we can calculate the distance from B to M, okay, and that is nothing but our rod length L. Distance from B to M is our length of the rod, that is our L, and we can also calculate with respect to their coordinates. We can say distance from B to M is rod length L, or with respect to their respective coordinates, we can say our RMB will be equal to RM minus RB, giving us R cos of omega t, comma R sine of omega t minus L cos of alpha minus, and this is 0, 0, h. And magnitude, we can say that our RMB, its magnitude will be equal to our R cos of omega t and whole square plus R sine of omega t whole square plus, this is minus L cos of alpha minus h whole square and its square root. And this entire is nothing but our equal to L. And we can write it, this will be our r square, and this will be cos square omega t, and this will be r square and sine square omega t. So r square we can take common, so this will be coming as cos square plus sine square, which will equal to 1. So we can write simply it as r square plus minus we can take as common, so this becomes L cos of alpha plus h whole square is equal to L square. And we already know our r, so we substitute it. R is our L sine of alpha whole square plus L cos of alpha plus h whole square is equal to our L square. Now if you open it, we are going to get this as our L square sine square alpha plus L square cos square alpha plus 2 LH cos of alpha plus h square is equal to our L square. And from here this sine square and cos square will be giving us 1, so we will be left with our L square only. So we get this L square plus 2LH cos of alpha plus h square is equal to L square. Here this L square and L square cancels out, so from here we can write, if we take h as common, so this comes as h plus 2L cos of alpha is equal to 0. Therefore we can say that either our h is equal to 0 or our h is equal to minus 2L cos of alpha. And if h is equal to 0, we get that our b coordinate will be equal to 0, 0, 0, and which basically means that these are the same coordinates that of our a, or we can say a and b are going to overlap, and which actually is contradicting. Okay, we can say which is contradicting, which is contradicting, which contradicts basically, and thus we can say that the value of h is equal to minus 2l cos of alpha. So from here we can say that our b is going to have 0, 0, minus 2l cos of alpha. These are the coordinates of our b, and we already know that our mass position, that is our rm, mass position, that is rm, is our is L sine of alpha cos of omega t, comma L sine of alpha and sine of omega t, and this is minus L cos of alpha. Now we come to the important part which was asked for us, is our velocity as well as momentum. Yes. So next is our velocity and momentum. So angular velocity so let us say our angular velocity that is omega is equal to omega and our k unit vector. Therefore velocity of the mass that is our v will be equal to angular velocity and our position vector of our mass. So we substitute it. Omega is our omega k unit vector cross, we are having this as L sine of alpha cos omega t, and this is our I unit vector plus L sine of alpha sine omega t j unit vector, and this is our minus of L cos of alpha and k unit vector. And we have to find out their cross product. So okay, therefore we can say that our velocity will be equal to this will be coming as we have k cross I and k cross j and k cross k. Okay, k cross k will be giving us 0, and we will be left with our k cross I will be giving us j, and k cross j will be giving us minus of I. Okay, so we can write this as minus L omega sine of alpha sine of omega t, comma, this will go L omega, and we have sine of alpha cos of omega t and 0. Okay. Now we find out the linear momentum. So we can say linear momentum that is our P is equal to mass into velocity. Okay. There will be no effect on the coordinate system, so we get our linear momentum P will be equal to our mass m, and rest is going to remain same, minus L omega sine alpha sine of omega t, and we have this as L omega sine of alpha cos omega t, comma 0. And now we come to the angular momentum. Angular momentum about point A. About point A. And for that we need the position vector, that is RMA, and A is our origin, so that we can say our RMA will be equal to our nothing but our Rm, because A is at origin. So we get this is L sine of alpha cos of omega t, and comma L sine of alpha sine of omega t, and minus L cos of alpha. And the angular momentum equation with respect to A will be equal to our RMA cross P, and P, let me write in terms of the vectors. We can say that our P, it can be written as, we can take L omega sine of alpha is common, so this comes as M L omega sine of alpha, and we get this as minus sine of omega t I unit vector plus cos of omega t j unit vector. Now we can just easily substitute it. Okay. So we get angular momentum with respect to point A will be equal to, let me write in the form of our I, j and k, and our I is our L sine of alpha cos of omega t and okay, so I is our L sin of alpha cos of omega t, J is our L sin of alpha sin of omega t, K is minus L cos of alpha. And for our P, we can write this as our minus ml omega sin of alpha and sin of omega t. And okay, next comes as our ml omega. We have sin of alpha and cos of omega t and 0. So in this case, we are here interested in our k unit vector only. So we can say our k unit vector that will be coming as m L square omega, and this will be our sin square and cos square, and other side will be also our sin square and sin square alpha and cos square alpha. That will be equal to 1. So we can write that our k unit component will be giving us m L square sin square alpha, and therefore we get our angular momentum with respect to A will be equal to m L square omega sin square alpha and k unit vector. There is other way also to find out, because the distance r, or we know that our angular momentum with point A will be the moment of inertia of with respect to point A and its angular velocity, that is omega, and our IA will be equal to mass into a radius square multiplied by our omega, and our radius we already know is our m, and this is our L sin alpha whole square and multiplied by omega. So we are going to get the same result, that is our angular momentum with respect to point A will be equal to m L square sin square, and omega is with respect to k unit vector. Okay. So in this case, this is sin square alpha. From this equation we can clearly see that our angular momentum A is dependent upon the mass, which is constant, length of the string, which is constant, alpha angle, which is also fixed because it is rotated in the, you can say, constant radius, and angular frequency is also constant. So which basically means that it is having a constant magnitude and direction. Constant magnitude and direction. Now let us find out with respect to point B. Same calculation, but with respect to point B. Angular momentum about point B. And so we can write that our LB will be equal to our R MB cross P, and our RMB will be equal to, that is our RB is our 0, 0, minus 2L cos of alpha. So our RMB will be equal to our L sine of alpha cos of omega t. Then it will be coming as L sine alpha and sine of omega t, and it will be L cos of alpha. And we are interested in the cross product, so you can write that the cross product will be our I J K, and we can write this as our L sine of alpha cos of omega t, L sine of alpha sine of omega t, and this will be L cos of alpha. And here we get this as minus ml omega sine of alpha sine of omega t, and this will be ml omega sine of alpha and cos of omega t, and this will be 0. And we can say this will be our angular momentum LB. Okay. So we get angular momentum LB will be equal to, and our I unit vector will be equal to our M, that is with negative sign, ml square sine alpha cos omega t. So this comes as minus ml square omega sine alpha cos omega t, and we have this as I unit vector, and then it will be our plus minus m L square omega sine alpha cos alpha and sine of omega t j unit vector plus m L square omega, and this will be a sine square alpha and k unit vector. So now we can find out its magnitude, and its magnitude will be equal to, this comes as our This will be our square, that is sine square cos square omega t, and here also it will be sine square cos square and sine square omega t. Okay, so we will be left with and this is our sine square omega t. Okay. And this will be under the square root. So from the first two part, and this will be because these two terms will be same here as well as here. So we can take this as common. This will be sine square plus cos square, which will equal to 1. And this will be coming as our sine square alpha and cos square alpha. Okay. So we can write this will be equal to our m L square omega, and we will be left with sine square alpha cos square alpha plus sine 4 times alpha and its square root. And we can take sine square alpha as common, so this will be our sine square plus cos square plus sine square. Okay, so we get its magnitude will be equal to over m L square omega and giving us sine of alpha, which is our constant magnitude. So let us check the options given to us. So it is given that first option LA and LB are both constant in magnitude and direction. Okay. But here, okay, I forgot to take the direction of our last part. And the direction is varying with our I as well as j. So we can say magnitude is constant, but direction I and j unit vector or components varies with time. Therefore, direction changes or not constant. Direction changes. Okay. And yes, so we come to the first option. Our LA is constant, but B is not constant, so option A is wrong. And LB is constant in direction, this is also wrong. LB is constant, this is also wrong. So only option 4 is correct. Four is correct. This was quite lengthy actually. But anyways, next question. It states that the angular speed of a truck wheel is increased from 900 rpm to 2460 rpm in 20 seconds. The number of revolution by the truck engine during this time is, assuming acceleration to be uniform. So we are having a initial angular velocity and we are giving a final angular velocity and time is given to us. Okay. And this is revolution per minute, time in seconds, so we have to convert into seconds. Okay, so we start with our initial angular speed. Initial angular speed, let us call this as omega naught, which is about 900 rpm, and we can write this as our 900 and 2 pi upon 60, okay, radian per second. And final angular speed is our omega, which is our 2460 multiplied by our 2 pi upon 60, okay, and this comes as radian per second, and this is also radian per second. And we can find out our angular acceleration. You can see our angular acceleration, that is our, or that we can use our omega is equal to omega naught plus alpha multiplied by t. So we get that our alpha is equal to omega minus omega naught divided by t, and this comes as 2 pi by 60. We can take as common, so this comes as 2 pi by 60. Time is 26, and we get this as 2460 minus 900, and this alpha can be approximated as 6.28 radian per second square. So from here we can find out our angular displacement. We can say the angular displacement that is our theta will be equal to omega naught t plus half alpha t square. We know all the values, so we can write our theta. Omega naught is our omega naught is our 900 2 pi by 60 time 26 plus half alpha is our 6.28, and this is 26 whole raised power square. So we get this theta will be approximately equal to 4574.16 radian. and number of revolution, that is our n. Number of revolution, that is our n, will be equal to theta upon 2 pi, and this comes as our 4574.16, 2 pi approximately equal to 7 to 8. So this is our 7 to 8. Next question. So this states that the following bodies: 1 a ring, second a disc, third a solid cylinder, fourth a solid sphere of same mass m and radius r, are allowed to roll down without slipping simultaneously from the top of the inclined plane. The body which will reach first at the bottom of the inclined plane is. So we have to find out whether it will 1, 2, 3 or 4. So in this case, we can use the standard formula for our acceleration, and that acceleration is given as a. So we have given that it is rolling, so it means rolling without slipping. The linear acceleration that is our a is given as g sine of theta, and we have 1 plus I upon mr square. And we can derive the relationship also. For that we are going to use conservation of energy. Okay, so let me derive it. So we can say energy conservation So the potential energy at the top, will be equal to mgh, and we can say that our h will be equal to s sine of theta, and kinetic energy at the bottom it will be kinetic energy translational plus kinetic energy rotational. So we can write this will be equal to over half m v square plus half I omega square, and there is a rolling without slipping, therefore we can put our omega is equal to v upon r. So this comes as our half m v square plus half I, and this comes as our v upon r whole square. So this gives us half v square m plus I upon r square. Now energy conservation, we can write that our mgh is equal to half m v square, and m plus I upon r square. So from here we get that our v square is equal to 2gh 1 plus I upon mr square. And for constant acceleration, you can say for constant acceleration, our v square is equal to 2as, because initially it is at rest. So v square minus u square is equal to 2as, or v square is equal to 2as. So we get that 2as is equal to 2gh upon 1 plus I upon mr square, and our h is equal to s sine of theta. So we can write 2g s sine of theta and 1 plus I upon mr square, and here is 2 and 2, s and s goes away, so we get our acceleration A is equal to g sine of theta 1 plus I upon mr square. So you can just remember this formula, or we can drive it also. So everything will be dependent upon this I, because everything is fixed, theta is fixed, g is fixed, m and r are same. So we have to find out the ratio, this particular ratio we have to find out. So we start with our ring, which is first body, that our ring, our moment of inertia I is mr square, therefore I upon mr square will be equal to mr square upon mr square. This cancel out, giving us 1. And second is our disk, which is having I is equal to half m r square, giving us as I upon mr square will be equal to 1 by 2. Then we are having solid cylinder, which is our I is equal to 1 by 2 mr square. So we get I upon mr square is equal to 1 by 2. And finally we are having solid sphere, which is even I is equal to 2 by 5 mr square. So we get I upon mr square is equal to 2 upon 5. So we can compare their accelerations. So we can say acceleration of the ring will be equal to g sine of theta 1 plus 1, giving us g sine of theta divided by 2. And we have our acceleration for the disk, which is g sine of theta 1 plus 1 by 2. And this gives us 2g sine of theta divided by 3. And solid cylinder is same, so we can say a solid cylinder will be coming as 2g sine of theta divided by 3, and sorry, it is solid cylinder, and we have solid sphere, which is our, it will be coming as 5g sine of theta divided by 7. And we have to find out the body which will reach first. So we have to find out the time taken for the bottom. Okay. And with respect to the acceleration, we can say that the acceleration for the sphere is greater than acceleration for the disk. Disk and our solid cylinder is same, which is greater than our for ring. This is the order of our acceleration. Now we find out the time to reach the bottom. Which is our s is equal to ut plus half it square. S initially is u is 0, so we can say that s is equal to half a t square, and from here we can say that our t is equal to 2s upon a and its square root, and s is our constant part here, so we can say our t is inversely proportional to 1 upon a. So largest acceleration is going to have the smallest time. So largest acceleration is our sphere. The sphere is going to have a smallest time. So we can say time for sphere is smallest. So option 4 is correct. I think it was 4 only, solid sphere. Yes, solid sphere. 4 is the correct one. Next question. It states that a sphere of mass 2 kg and radius 0.5 meter is rolling with an initial speed of 1 meter per second, goes up the inclined plane, which makes an angle of 30 degree with the horizontal without slipping. How long the sphere take to return to its starting point A? So basically, the angle of inclined plane is given as 30, starting point is given as A, and body is rolling up the inclined plane, and suppose it reaches the highest point, that's a B, and then it is going to return back. So we have to find out the time taken to return to the starting point A. Okay. And initial speed is given to us. So here once again we are going to find out the acceleration of the sphere, the same formula which we derived. Okay. So we can say that sphere rolling without slipping down the inclined plane. Okay, we have to remember that. So we can say sphere without slipping down the inclined plane. And its acceleration, that is linear acceleration A, will be equal to g sine of theta 1 plus I divided by mr square. And we are a solid sphere, so we can say our I will be equal to 2 by 5 mr square. And so from here we can say our I upon mr square is equal to 2 upon 5. Therefore, A is equal to our G, that is 9.8 sine of 30, and this comes as 1 plus 2 upon 5. This gives us acceleration approximately equal to 3.5 meter per second square. And this is down the inclined plane A acceleration. Okay. And it is also mentioned that the sphere is rolling up the inclined plane, and so we can say that since the sphere is rolling up the inclined plane, okay, but acceleration we found out when it is rolling down the inclined plane. Okay. So therefore, from here we can say that acceleration A will be equal to minus 3.5 meter per second square. Okay. And this is for when it is rolling up the inclined plane, because the acceleration is going to remain same. And we can say that our time to reach the highest point and at highest point its final velocity will be equal to 0, so v will be equal to 0. Therefore, we can use the equation that v is equal to u plus at. Now our v is equal to 0, initial velocity is given to us as 1, so this will be plus minus 3.5 times, let us suppose time is t1. Therefore, we get our t1 will be equal to 1 upon 3.5, which is approximately equal to 0.2857 seconds. And this time is up the inclined plane, and the down the inclined plane, I mean the total time will be equal to twice of t1. It's simple, because yes. So let me write this. We can say for rolling without slipping, the acceleration magnitude and here acceleration we are talking about the center of mass acceleration, which we have calculated as a. So acceleration magnitude is same up and down, up and down, because up and down the inclined plane. Because during the pure rolling motion, whatever adjustment is to be made will be made by the friction, which is going to adjust according to the, you can say, the which is going to adjust to provide the necessary torque. Okay. So it means when it is moving down toward the point A, acceleration we calculated is as plus 3.5, and when it is moving up it will be minus 3.5. Okay. And therefore total time that is of capital T will be equal to T1 plus T2. Okay, T1 is down the inclined plane, T2 is up the inclined plane, which is same, so this comes as twice T1 and will be equal to 2 times 0.28. So we get total time T will be approximately equal to 0.57 seconds. So option number 3 is correct. Correct. Next question. It states that a thin circular ring of mass m and radius r is rotating about its axis with the angular speed omega. Two particles having mass m each are now attached diagrammatically opposite point. The angular speed of the ring will become. This is quite simple. In the first case we are having only a ring and mass, and the second case we are having a particle as well as the particle of mass small m, and this will be based on our conservation of angular momentum. So our initial angular momentum that is our L initial will be equal to moment of inertia for the ring and our omega. So we get that our L initial will be equal to moment of inertia of the ring is our mr square and omega. Now our final moment of inertia final angular momentum and final angular momentum will be for the system, and the system will be our ring plus two particles. Therefore we can say that our L final will be equal to moment of inertia final and its angular velocity omega prime, and our moment of inertia of final will be equal to moment of inertia for the particle plus moment of inertia for our disk or ring. And for particle we have two particles, so that will be 2 times mr square plus ring is our mr square. Therefore we get our angular momentum final will be equal to, we can take r square as common, so this comes as 2m plus capital M and omega prime. Now we can equate them. So we get our L initial is equal to L final, and N initial is our mr square omega, final is our r square 2m plus capital M and omega prime, and this r square cancels out, so we get our omega prime is equal to m upon twice m plus capital M multiplied by omega, and this comes as omega, and option number B is correct. Correct. Next question. It states that consider a uniform wire of mass m, length L. It is bent into a semicircle. Its moment of inertia about a line perpendicular to the plane of the wire passing through its center is. Okay, so we have a wire and which is bent to form a semicircle. So first of all, let us try to understand the geometry of the semicircle. Geometry of semicircle. So we have a wire and whose length is given as L, and this wire is bent into semicircle. And if R is the radius of semicircle, radius of semicircle is suppose small r, then we can say that our length will be equal to pi times r. From here we can say our r is equal to L upon pi, because initially we were having a length wire which is having a length L, and then it is bent in the form of a semicircle, something like this. And So we can say that the linear mass density, suppose that is lambda, linear mass density, that is lambda, will be equal to mass oblique length of the wire, that is L. Now we have to find out the moment of inertia for the semicircular wire. And here, excuse me, here we have to remember that the wire, the axis is passing through the center. Okay? And here the center is basically, you can say, center of the complete circle, not the center of the mass. Okay, so which means that we have a wire which is bent in the form of a semicircle, and if we complete the circle it will be something like this, and its center of this complete circle will be this part. So the axis is passing through this O, not through the center of mass. And we can say that, let us draw an axis. So this is our x-axis and y-axis, and this center O, it is having a coordinate of 0, 0, 0. Okay. And with respect to theta and its axis of rotation will be along z axis, okay, which is basically this is z axis, which is perpendicular to O. Okay, so we can say that semicircle is in xy plane with center O at origin, which is 0, 0, 0. Therefore, the axis of rotation, axis of rotation along z axis, and with respect to angle theta, we can say that semicircle extends from theta is equal to 0 to theta is equal to pi. So let us consider a small element dl, so we can say consider a small element dl, which will be equal to r times d theta. So small element basically means, this is center, so we consider a small element, this is our dl, radius is r, and this angle is our d theta. So this mass of this small element, or sometimes it is also called as a differential element. So we can say mass of differential element that is about dm will be equal to lambda times dl. Lambda we know our mass of the total length, dl is our r d theta, and r is our L upon pi. D theta. So here this L and L cancels out. So we get our small differential element, mass of differential element is equal to m upon pi d theta. Okay. And the moment of inertia contributed by this differential element. Moment of inertia contributed, let us suppose that is about di, which will be equal to dm r square, and we can say that our di will be dm is our m upon pi d theta, and our r is our L upon pi, and this comes as whole square, which can be written as m L square upon pi cube d theta. Now we can just integrate for a complete half circle. So we can say integration 0 to pi, we have this is m L square pi cube d theta, and this will be coming as our m L square pi square, and this will be only theta and multiply by pi. So this is cube. So this cube goes by this pi, and we are left with ml square upon pi square. So we have ml square upon pi square. Option 3 is correct. Is correct. Next question. It states that a solid cylinder of mass m is wrapped with the inextensible light string and is placed on a rough inclined plane as shown in the figure. The frictional force acting between the cylinder and the inclined plane is, the coefficient of static friction is 0.4. So in this figure, you can clearly see there will be a force of tension acting in upward direction, and this is solid cylinder will try to roll in the downward direction. So we are going to have force of friction that will be acting in upward direction. Okay. This is the basic forces other than your mg and everything. Okay. And let me draw the mg also. It will. So we are going to have mg. It's two components. This angle is theta, which is 60. So we are going to have mg cos of theta, and we are going to mg sine of theta. Okay. And there will be normal, but that the motion is only down the inclined plane, so we are going to just ignore it because we are not interested in that. Okay. And okay, normal we require because there is a friction part involved in it. Therefore, let me draw the normal. So we can say our normal n will be equal to mg cos of theta, mg cos of 60, and this gives us our half mg. Therefore, maximum static friction maximum static friction, which is our F max, will be equal to mu s multiplied by n, and which gives us that F max is equal to mu s is over 0.4 multiplied by n. N is our 1/2 times mg, and this comes as our mg by 5. And let's find out our equilibrium conditions. And the equilibrium conditions. And the equilibrium condition means there will be no translational and no rotational. Okay, so we start with our translational equilibrium. Translational equilibrium. Okay, so there will be a downward force mg sine of theta, and there will be two forces up the inclined plane, that is a T as well as our F. So we can say that for translational equilibrium, we can write that our mg sine of 60 will be equal to tension T plus friction F, which gives us that our T plus F is equal to √3/2 times mg. Now we come to the rotational equilibrium. Rotational equilibrium. So there will be two torques. One torque will be because of the tension, and one torque will be because of the friction. And one will be our clockwise, other will be our counterclockwise. Okay. So we can say that torque due to tension let us call this as T of R, and torque due to friction let us call this as F of R, and net torque should be equal to 0. So you can say net torque will be equal to 0. Oh, 1 second. Let me write the formula itself, otherwise it will create a problem. So torque to tension T will be equal to tension T multiplied the perpendicular distance, that is radius R, and torque due to friction force F will be equal to frictional force F multiplied by perpendicular distance R. So net torque will be equal to 0, or we can say T of R minus F of R is equal to 0, giving us T is equal to F. So now we can use equation number 1. So we can say from equation 1, from 1 we have our F plus F is equal to square root of 3 divided by 2 and mg. This gives us that F is approximately equal to 0.433 times mg. So this is the our friction. Okay, but we know that the maximum friction we just found out is our 0.2 times mg. So let us check the feasibility, because we are having two values of friction. One is our 0.4 times mg and the other one is a maximum friction, that is our 0.2 times mg. So only one value of friction we have to take. So let us check the feasibility. And we can say that our value of F is greater than our maximum value of friction. Okay, we can say that 0.433 mg is greater than 0.2 times mg. It means the required value of friction exceeds the maximum available static friction. Okay. So from here we can say the required value of, or rather the required friction exceeds the available static friction. Available static friction. Therefore, from here we can draw the conclusion that cylinder cannot be held in equilibrium. Therefore, cylinder cannot be held in equilibrium. Or we can say that it will slip. It will slip. Therefore, the frictional force when slipping occurs frictional force when slipping occurs. Okay, and we know that when the cylinder starts to slip, the frictional force transitions to kinetic friction, okay, because it is now slipping. Therefore, we can say that our frictional force when slipping occurs it transitions to kinetic friction. And in this case we can for the sake of simplicity, we can say that our kinetic friction is equal to our static friction, which is about 0.4. Okay. Because where only our static friction is given and slipping is going to take place, we can just make a presumption that kinetic friction is equal to the static friction. Therefore, our frictional force F will be equal to kinetic friction and normal, which comes as 0.4 multiplied by 1 by 2 times mg, and we get that F is equal to our mg by 5. So we have option number 3 is correct. Option 3 is correct. Okay. And if this condition is not satisfied, so obviously there will be equilibrium. Okay. Then it will be just change on the, you can say, the solution. So this part, the comparative part, is very important. This is basically also, you must have solved many questions based on the boxes which are just sliding on the rough horizontal plane. Okay. So this particular question is somewhat related to that concept also. So this completes all the 12 questions. So this was for 2021 part 1. Remaining questions we are going to solve for the part 2. Thank you.